Okay. So the depiction here is from August 28th, 2005. And the situation was that there's a Category 5 hurricane just offshore. And the location is Waveland, Mississippi. And maybe David and Kimberly King, living in Waveland, may have known that they could have issues from hurricanes if you live in a city called Waveland. That's their first clue, that they have to perhaps do something. And you can see that they actually had their shutters that they were about to deploy on their windows. And they were told they were in an evacuation zone. Category 5 was coming, and they needed to evacuate because of the storm surge. They lived about a half mile from the beach. So they boarded up. They did the right thing. They left town. And when they came back a month later, this is what they had left. Yeah. So what had happened was Katrina made landfall, and there was about 110, 120 mile per hour winds, but also a 15-foot storm surge that carried away everything. So they did the right thing. Their possessions were lost, but they stayed safe. Unfortunately, 200 people in Mississippi drowned, some of their neighbors, and 1,300 people in Louisiana drowned in about a day from Katrina. And this is from a hurricane. Yes.
Please, everybody, please mute yourself. I think there's so much echoing. Someone is not muting. Please mute yourself. Thank you.
Okay.
Thank you.
Keep going? Okay. All right. So, from a hurricane that every single person in the United States knew was coming, 1,500 people drowned because they either chose not to leave or they needed help to get out and the help never arrived. So this type of situation, devastating hurricane, making landfall, a lot of people drowning, is what keeps us up at night at the Hurricane Center. So with that kind of preamble of why it's important, I want to discuss what we do at the Hurricane Center, what our mission is, what the hurricane risk is, and then a little bit about the different folks at the Hurricane Center, and then specifically when it comes to the hurricane analysis and forecasting, and then finish up with what's new for this year and following years. And if you have any questions at any point, let me know. So I want to give you a good, thorough overview about what's going on. So the mission at the Hurricane Center, to paraphrase what's shown there, is we analyze and forecast hurricanes and marine weather so that people can safeguard their property and keep themselves safe. Come on in. All right. And the picture here shows Rick Knabb doing one of the briefings over the last 5 years. And you may have heard that Rick just retired. He went back to the Weather Channel in Atlanta. And we've got a number of vacancies. So I'm not sure if I don't get home on time, there might be nobody left at the Hurricane Center. So I better get back soon. We actually have 4 out of the top 6 management people leaving by the end of the year. So at the Hurricane Center, we have 50 feds and 15 contractors. The Hurricane Specialist Unit is 10 full-time hurricane forecasters. We have a Navy civilian hurricane forecaster and myself that do the day-to-day hurricane predictions from mid-May to late November. We have 18 forecasters in our tropical analysis forecast branch, so they do the marine prediction. So analogous to what OPC does here for the higher latitudes, TAFB does for the Gulf of Mexico and the tropical Atlantic and Pacific. And we have 8 folks in our technology and science branch, which I am officially a part of, that keeps everything running and leads the development. So we're not a huge organization, a bit smaller than EMC, a bit bigger than OPC. So when it comes to TAFB, I want to discuss some of the products and issues that they have and what we've been accomplishing. So first off, the marine forecasting in TAFB is open ocean, so it's not coastal. So what we're dealing with is the deep open ocean. Our main customers would be the Coast Guard, the cruise boat industry, and the merchant marine vessels. and any very large recreational vessels. The areas we have responsibility for, so our high seas extend out to 35 west in the Atlantic and out to 140 west in the Pacific. We still have responsibilities south of the equator, but next month Peru is going to be taking those over. And then we have more detailed forecasts we provide in our offshore zones in the Atlantic, Caribbean, and Gulf of Mexico. And over the last year, we've had experimental offshore zones for the East Pacific along this main corridor where most of the boating activity is shown. Probably more importantly is the development the last few years for the gridded forecast. So we switched to the National Digital Forecast Database, populating it through GFE, the gridded forecast editing process. And this occurred about 5 years ago, and it's been a big revolution in how we produce the forecasts and how we provide the forecasts. And I know OPC is in the midst of those steps as well, and WPC is embarking on that over the next few months. But we're able to provide gridded forecasts out through 6 days of surface winds, significant wave heights, and hazards. So that would be gale force, storm force, hurricane force, wind warnings over the open ocean. So an example here for the wave heights and down below the winds. And we try very hard to make sure we have consistency between our hurricane side of the shop and our marine side of the shop. And it's not easy because they're being developed on separate platforms in part. So our hurricane side. So our hurricane responsibilities are a bit larger than the marine. So if it's a hurricane or tropical storm or subtropical storm anywhere in the Atlantic, so even north of 31 North, where OPC's borders start, our hurricane specialist unit has responsibility for that, as well as hurricane duties out to 140 West in the eastern North Pacific. So it's a gigantic geographical domain. We're very fortunate, though, that we have the tools and technology to both monitor what's going on as well as forecast. So because it's phenomenon-based, we have to identify when these features begin and when they end. And where we do have a definition of what a tropical cyclone is, which is the generic term for hurricane, tropical storm, depression, and we have these definitions that we try to employ, often they're difficult in real time to decide what is sufficient to call it a tropical cyclone. So for example, having organized thunderstorm activity. It's a fairly ambiguous definition. We use the Dvorak technique as one way to quantify that comes out of the satellite analysis branch, as well as the TAFB itself. And even the issue of baroclinicity. I mean, how much baroclinicity is there inherent before you'd say something's frontal? And so some of the biggest discussions at the Hurricane Center are when do we start advisories, when do we stop issuing them? And that can be the most difficult. And even the definitions of categories between depression, storm, hurricane, and the Saffir-Simpson wind scale ones, we have these very precise values for tropical storms, 39 to 73 miles per hour. But our ability to actually note what the strongest winds are is much more uncertain that would imply. Because our ability to know the peak winds or intensity is really to about 10%. So if I would start over, I would say, well, let's make this 40 to 75, because that implies way too much accuracy than what's actually available. Okay, so we have a little quiz for everybody here. I don't know how we can do it online. But when you look at the last 50 years of impacts in the United States, there's 4 main hazards that affect folks and cause property loss as well as loss of life. You have the wind-caused damage, like this picture I took after Hurricane Andrew in 1992, storm surge from Katrina, isolated tornadoes in the periphery, and rainfall inland flooding and flash flooding. So you have to vote. So you have to vote on what causes the most fatalities in the United States. Okay, so who thinks that storm surge causes the most fatalities in the United States? About half. Who thinks it's the wind caused damage? All right, 1 or 2 votes. Who thinks it's the isolated tornadoes? So there's nobody here from SPC. Not even Greg Carbon's here today. So you're right, it's not that. Who thinks it's the inland flooding and flash floods? Oh, about half. Well, if you had said water, you're right. So it turns out that 80% of all the fatalities in the United States are either offshore due to ships, folks in the surf zone, rainfall-induced flash flooding, or storm surge. So the single greatest hazard itself is storm surge. Half the fatalities in a 50-year sample were due to that. And that's one of the reasons why there's been such big efforts in the Weather Service and the Hurricane Center specifically to develop storm surge warnings. So I'll go into that into a bit more detail. But yeah, it's not the wind, it's not the tornadoes. Rainfall-induced flooding is a big component, but 80%, 85% is due to water. So a little bit about hurricane risk or vulnerability. Risk for a particular event is the correspondence between incidents, how often does it occur, and exposure, how many people or structures are in harm's way. So you have a place like South Florida, where I live, down in Miami, where you have drastically increasing numbers of people living in harm's way, coinciding with a whole bunch of hurricane strikes historically. That means it's a massive amount of hurricane risk or vulnerability. But even if you don't get a lot of hurricanes, so let's say Rhode Island or Connecticut, that can still be a huge risk from hurricanes because you can get strong ones up there, but the incidence is so low that people may not know what the true danger can be. So I'll show you how the forecasts have gotten better in general, but keep in mind the backdrop of the hurricane vulnerability in the United States, as well as everyone in Central America and the Caribbean, keeps going up because coastal populations are skyrocketing. Everyone loves to live near the ocean, but you have to be prepared occasionally. Okay, so that's a little bit about who we are at the Hurricane Center and also some of the societal issues. I want to switch gears to the tools. What are the observations that we make use of on a daily basis? And then I'll get to the forecasting aspect next. So on a day-to-day time scale, we've got lots of in-situ observations and remote sense data. We've got ships out over the open ocean through the Volunteer Observing Ship Network. We have both moored buoys and drifting buoys that we're getting pressure or sea surface temperature or wind data from. We also get scatterometer data. I'm showing here the old QuickScat data that was available, but now we have the ASCAT scatterometers to make use of, as well as all the station data, mainly at airports. So on a synoptic scale, we're very rich. We've got lots of observations to look for. Unfortunately, though, for example, when a hurricane is going through the shipping lanes, for some reason, all the ships tend to move away, which is good for the ships, but makes it tougher for us to figure out what's going on at the ocean surface. So especially the scatterometer data has taken on increased importance over the last few years. And so to supplement that, we have the constellation of the polar orbiting satellites and the geostationary. And so I'll show you one example of how we make use of the geostationary satellites. So this is infrared over the eastern Pacific. There's a tropical storm out here, and part of our requirements are to know the position to the nearest 1/10 latitude longitude every 6 hours. These are in 2-degree grid boxes. And the reason it's important to know that precise a location is when a hurricane gets strong, it's very mesoscale. So you need to know where the location of the center is because that's where the strongest winds are, or very close, within a few dozen kilometers. Now, if you're just looking at a linear gray infrared image, you might say, well, maybe the center is somewhere in the middle of that cold cloud top canopy. Of course, you could color enhance it to look at what the coldest cloud tops are, and this aspect makes it look a little bit lopsided. Maybe the center is right underneath that -80 Celsius cold cloud tops. But it makes it very difficult at night, especially when we don't have the visible imagery available. The shortwave infrared helps, but once you get any cirrus, you can't see through the cirrus. So fortunately, we pair the geostationary imagery with the polar orbiting. So this example from an SSMI from 85 gigahertz shows in red the very thick water clouds, or the mixed phase clouds in red. And in blue, it's the very low stratus or strato Q. And you can clearly see the spiral bands in the low-level features showing up there. So this allows one to quickly see, well, the center's here. And so if you just looked at it from a geostationary platform, you get a very different answer. And again, we need to know quite precisely where the center of the storm is. So on a regular basis, we get independent estimates of both where's the center of the storm and how strong is it from two different agencies. So we get it internally from the Tropical Analysis and Forecast branch, but we also get it every 6 hours from NESDIS Satellite Analysis branch up on the 4th floor. And so getting these independent estimates are crucial because the hurricane specialist blends them together, and in general, you combine independent estimates, you get a better final answer of where is it and how strong it is. To me, it's still amazing that a technique invented by Vern Dvorak up here 40 years ago is still the de facto best tool for analyzing the intensity of hurricanes even today. So we're fortunate we also have access to the hurricane hunters. So the 10 C-130s that are operated out of Keesler Air Force Base are routinely used to fly into a storm. And NOAA's Aircraft Operations Center in Tampa that are just moving to Lakeland. They have 2 Orion P-3s that also fly through the center, and then a Gulfstream 4 jet that flies around the storm. And I was very fortunate early in my career to be able to be on many of these missions when I was at the Hurricane Research Division. So the methodology of flying is typically you do what's called a figure 4 and alpha pattern, where you fly a radial into the center, keep flying all the way back through, fly downwind, and then fly another diameter through the storm there. And the idea is to answer 3 questions. Where's the center of the storm? How strong is it? That is, what are the peak winds at 10 meters above the ocean? And how large is it? How far do the hurricane force winds and tropical storm force winds extend from the center? So it's difficult, based on satellite techniques today, to get that. Scatterometer can help with the 34 knot winds, but really not as much for 50 and definitely not for 64 knots. Okay? Geostationary imagery can't help you at all, and so it's a big gap for us. How do we measure the size of storms? Yeah?
Do you use rain-contaminated winds from the scatterometer? You must if you're getting anything into the hurricane, but
Yeah.
they're known to be uncertain, so I wonder how you guys handle that.
We do look at all the vectors that are available, and we look at the ambiguity solutions as well, because sometimes the automated solution chooses the wrong vector, and the human analyst can pick out which is correct. But you're right, sometimes it's ambiguous if it's showing 50 knots from one of the scatterometer winds, whether that's wind or rain or both. And so it's often a little subjective. But we do look at the rain-flagged vectors as well. So one of the unique tools that was instrumented on all the aircraft is the step frequency microwave radiometer. And so this allows, through a passive sensor equipped on the wing, to measure the ocean surface winds. And it does that by using 4 different frequencies in a microwave spectrum, because when the ocean is churned up and there's lots of foam and spray in the air, it emits a little more microwave radiation. So it's not enough to cook a hot dog on board the airplane, but you can calibrate that microwave radiation that's being emitted and get a very accurate wind. And the nice thing is the signal-to-noise ratio is best for hurricane force. So this works great from category 1 to 5. It actually has problems at the low wind speed. Another tool that's been very helpful for looking at the synoptic scale are the GPS-based drop zones. And so we've now had them for about 20 years, and they're still used routinely, mainly in conjunction with the Gulfstream 4 jet. So the idea is the Aircraft Operations Center would take off with the Gulfstream jet, fly, circumnavigate the storm, sample maybe a mid-latitude ridge or any troughs that are going to be impinging upon a storm, and each dot location to drop a sonde. So those get assimilated into the global and regional hurricane models. At least we hope they get all assimilated, and the idea is that they can help with the forecasting. And one of the questions is, how can we perhaps use some of the drop sondes that are being launched by the Global Hawk that Jason's been involved with to help with the track prediction as well. And so that's, there's actually a meeting tomorrow to talk about UAS or Global Hawk usage for operational hurricane forecasting. So those are some of the tools we have. And if someone says, well, what's the most important observational platform you have? It's a very easy answer. It's the geostationary satellites. We could not do our job without the geostationary satellites. And so the new availability of GOES 16 is going to be an enhancement to what we already have. But they are crucial. We could not do our job without them. All right, so switch to forecasting. So I've talked about how we analyze storms and the key things we need to understand. Where is the storm? How strong is it? How large is it? So on the forecasting aspect, even before a storm forms, for the last few years we've been issuing tropical weather outlooks that are quantified. When I first joined the Hurricane Center 12 years ago, they were issuing these tropical weather outlooks that really weren't a forecast. It was just real ambiguous wording. But in the last several years, we've quantified it. Percent chance of forming within 2 days. In the last few years, within 5 days. And we've also been providing an area where if the storm forms, this is where it could form. And so we're trying to enhance our genesis forecasts. So this is before a storm forms. And I'll, at the end, I'll mention how we're providing a new forecast product to the public that is available before genesis. So once you have a tropical cyclone, obviously to a first order, it's being steered by the broad synoptic scale. So you're looking for variations in the Bermuda High, you're looking at any impinging shortwave troughs. And a generation ago, the best human forecaster could outdo any model. That's changed a lot. And so nowadays, our forecasters don't put a lot of their own body English into the track forecasting because of the extreme skill from the global models. So here's an example. This is Hurricane Ike from 2008. It's getting a few years old, but it's still very representative today. The white line is the observed track. So that's what we want to know in advance, but we never do. So instead, we have these models that are available every 6 or 12 hours. And so we have about 5 or 6 that are highly skillful. And so they're showing up as different colors here. Now sometimes you'll notice where there is a lot of agreement between the models. So for example, for these solutions, extremely tight packing. So we'd know that in general that the confidence would be higher, that the track forecast would be on par. But then you have situations like here, where you have spread all the way from Mexico to Ohio. Except for the 2 ending in O, they're not very similar. So that has a lot more difficulty in making a prediction. Another aspect is that sometimes forecasters will note where there's biases showing up. And so when Ike was reaching this northernmost point before coming back south, you notice all the forecasts are too far to the north. They had a systematic bias too far north. So a slick forecaster might say, well, I'm going to shift all my forecasts equatorward because of that bias. Well, the problem is that works until it stops working. So here, they were all too far south. So you can't get too cute in over-interpreting the model guidance, even for a single storm, because a perceived bias can change. One other thing is that the models could change dramatically from cycle to cycle, obviously. But our forecast can't do that. So the handoff from forecaster to forecaster is real important. And so whenever we're making a new forecast, we're looking very closely at what was the last forecast. So for example, when Ike was threatening Florida and the forecast was for Miami, you don't want to make the next forecast, hitting Jamaica or Savannah. That kind of windshield wipering around, the public loses a lot of credibility very quickly with what you're providing. And analogously, you don't want to say, okay, it's going to hit Houston on Saturday, And then you back it up. No, it's really going to be Friday. No, sorry, it's going to be Sunday. So that kind of tromboning back and forth in time is also problematic. So when we make changes, we tend to be conservative in the official forecast, because sometimes the models may show a change and then flip back. So an example of that is when the models all started going south to Corpus Christi here, but then they came back and it actually hit Houston. So being conservative sometimes works in your favor. Now, obviously, if there's a big change that has to be made, the forecaster does it, but that can be difficult to determine in real time. So the track forecasting itself has had incredible improvements in the last 30 years, 40 years. You can see, for example, a 3-day forecast in the 70s was about 375 miles error on average. And over the last 7 years, it's been about 100. So a massive increase or decrease in the forecast error just in 30 years. Now, it's not that you had a bunch of knuckleheads back in the 1970s and you have a bunch of Einsteins today. The forecasters are just as good today. But it's the global models being informed by the satellite data through the data assimilation. So that's why we're doing so much better today. All right. And because of these improvements in the 1990s, in 2001, they started doing experimental 5-day forecasts, and we went public with it in 2003. We have been doing forecasts out through 7 days experimentally, but we're not quite ready to start issuing those publicly. Don't quite think they're that good. To me, this is one of the biggest success stories in all of numerical weather prediction, this improvement over time. It's not the forecasters, it's the tools they're using. So just another example of this, because it's so dramatic. So in 1990, when I was in grad school, the average error for a 2-day forecast for a hurricane to hit the Alabama, Florida coast went all the way from New Orleans to Cedar Key. In the last few years, the average error is tiny. It'll only go from Mobile to the other side of Pensacola. So this has allowed for a much more precise warning area for us to let people know where the impacts are going to be, whether it's wind or surge. Okay, so another quiz. All right, see if you guys can do better on this one. What does a cone mean? All right, we use this all the time. We talk to FEMA about it. A lot of people still mess it up. So does the cone mean that that's the likely area of strong winds? Does the cone mean it's the likely location of the center of the hurricane? Or does the cone mean it's the likely area of strong winds, heavy rain, and storm surge, and/or storm surge? So you have to vote. Who thinks it's number one? It's the likely area of strong winds. Nobody. Okay. Who thinks it's number two? It's the likely location of the center of the storm. About half. Who thinks it's number three? It's the area of strong winds, extreme rain, and storm surge. A few. Okay. All right. You guys are wrong. That's okay. That's why I'm here. So it's the likely location of the center of the storm. So it's based upon the last 5 years' worth of official errors. And so when you do the deterministic forecast, a circle is drawn around each forecast point, and that represents the 67th percentile errors over the last 5 years. So the cone is updated every year, but it's the same for each storm for the whole season. So where a cone may be really long and spread out if it's moving fast, or squat if it's moving slow, the circles in the cone are the same every time. So we've talked about, well, maybe we should have a dynamical cone that shows less of an uncertainty if all the models are showing the same thing, or the opposite if they're spread out. Problem is that so many of the public, and I guarantee you, a sample of the general public would be a lot worse than what you voted. They don't get it now. So if we start making modifications to a product that a lot of folks misunderstand, it may not help. But we're going to continue to discuss that. So one way we are changing it this year is to include the size of the storm on the cone graphic. So it's making it a little more complicated, but we hope that it gets the point across that The hurricane force winds in red and the tropical storm force winds in orange extend way outside of the cone when you're looking at the short time ranges. So this year, you could see it for the active tropical cyclone we have today in the Pacific. This is what the cone's going to look like. So we've actually revamped the cone graphics completely, but included the size of the storm. So we hope that helps get the point across. The cone is more of an uncertainty of the track location and not an impact graphic. So if we're not going to show impacts on this, how are we going to show it? How can we tell them about the wind and the surge and the rainfall? So intensity. Intensity is the peak winds. How well have we been forecasting that? And it's a very complex process because it's the ocean sea surface temperature, it's the subsurface of the ocean down to the thermocline, it's the very heterogeneous air masses. We get these Saharan air layers that get into the vicinity of storms. Vertical shear, while our friends in Norman, Oklahoma love vertical shear with tornadoes, hurricanes don't like vertical shear. And they go through natural cycles of concentric eye wall formation that weaken the storm temporarily and then re-strengthen it, that are completely unpredictable today. So it's a much more difficult physics problem. It may be an order of magnitude more difficult than track prediction, which is essentially advection. And when you look at the forecast errors, and again, this goes from 0 to 5 days, and for the first 30 years on here, from the 70s, 80s, and 90s, there really was no improvement. No improvement in forecasting the intensity or the wind speed. But starting the last 10 years, we've had some substantial improvements. And a large portion of that can be due to the hurricane weather research forecasting efforts that have been led here at EMC. And so this has been exciting to see improvements, measurable improvements. But still, at a 48-hour time scale, when we issue watches or warnings, you have an average error of about 15 miles per hour. So what is that? It's a category. So if we're forecasting a category 3 to make landfall, the errors that we have at a 2-day time span really mean we're forecasting a 2, 3, or 4. And if they're having a bad day at the Hurricane Center, or if the bottom of the forecast has the name LANDSEA, you could be 2 categories off. So if you're 2 categories off, which happens about 5% of the time, you could be calling for a 3 and it either is a 1 or a 5. And you just have to look at the last 2 years. Tropical Storm Erica was forecast to be a hurricane hitting northeast Florida, and it fell apart completely. Joaquin, on the other hand, was forecast to fall apart and became category 4 over the Bahamas. So we have a long way to go still in improving the intensity forecasts.
Has the rapid intensification forecast gotten any better at time? That's an average of all.
Yes, it has. It has. There have definitely been improvements in our ability to forecast rapid intensification. It's more at the immediate time scale. Like if we tried to forecast rapid intensification between days 3 and 4, we have no ability yet. But for the next 24 hours, yes, we've improved. So we know that the forecasts are never going to be perfect. And so how do we include the uncertainty and start forecasting the impacts? Because you don't want to know, is the center of the storm going to be 50 miles away from me? You want to know, what are the winds at my neighborhood? You want to know what the storm surge, what the rainfall is. And so the approach that's been used over the last decade is to use the official forecast, shown here. This is example for Hurricane Bill. And the idea is there's a 1,000-member Monte Carlo simulation that's run every advisory. And all 1,000 of these are plausible representations of what could occur. And so they take into account the track errors, the intensity errors, and the size errors that could occur. And the nice thing is these are informed by the spread of the track model guidance. So if the track models are much closer agreement, these 1,000 members are likewise constrained to be in much better agreement. And after this is run, then you can just look at the wind fields from all 1,000 storms and come up with an empirical wind speed probabilities by thresholds. So you could have tropical storm force winds, 50 knots, and hurricane force. And so to me, this is an incredibly powerful product for the decision makers that have to make calls that are wind speed based. So let's assume you're in Boston and you're the school superintendent there, and your threshold for closing schools is 60 miles an hour, 50 knots. And we can't tell him or her that you're definitely going to have that or not. But if we can tell that person, well, you've got a 35% chance of those winds occurring at your school district. So, if it's a low value, you might say, well, why do it? But it's a low value of something very catastrophic happening that you may want to take action. And those decisions have to be made at those local levels or national levels. We don't make those decisions about evacuations or telling tourists to go home or telling schools to shut. But if we can provide better tools to help make those decisions, then I think we're helping out. So the same approach is being used for storm surge. Storm surge is even more, the errors in storm surge are even more tied to the exact track. And so you never want to look at one single storm surge run. So using a deterministic approach is just the worst way to go, and it would kill people, because a change in the track, a little 20 or 30 miles east or west, can make the difference between 5 meters of surge versus 0. So in this case, again, the operational forecast is used, and then several hundred runs of SLOSH, the Sea Lake Overland Surge from Hurricanes, is run. It's a simplified dynamical storm surge model. And the idea is to look at the inundation that can occur and provide that in 2 different products. First of which is an automated one we call the inundation map. And the idea is color-coded, where you could have up to 3 feet, 3 to 6, greater than 6, and greater than 9 feet of water above the ground. It used to be that the products from the Weather Service would talk about above sea level, above mean high or high tide, above NAVD 88. Forget it. How high is it above the ground where I live? It makes it very simple to convey the message. And the way it's provided, this is a 10% exceedance, or sorry, a 10% chance of at least these amounts of inundation occurring. We don't say that to the public. We say this is a reasonable worst case. All right? We're not saying this is the most likely. This is a reasonable worst case. Because in this case, what we're talking about is 10% chance, if you're living here at Cypress Lake, of your house completely going underwater. So we also have been doing, I'll skip to that. We've also been doing storm surge warning capabilities. And so this debuted last year experimentally, and I got to work with Jamie Rome and company. And the idea is to just simply paint an area along the coast and inland of where we think that at least 3 foot of water is going to occur, and have it as a watch within 48 hours where life-threatening storm surge could occur, and a warning that life-threatening storm surge is expected to occur within 36 hours. And we ran this last year, and it's in conjunction with the WFOs. We run it in GFE, we send it to the WFOs, they edit the grids, they send it back to us, and within 30 minutes we have a warning available. And so we're hoping that our determination as the National Weather Service of where you are in danger of drowning is going to be an important new tool. So I've been working with some of the OPC folks this last few weeks and helping with some of the training and going through the buttonology in case OPC has to be invoked for the backup capabilities for this new warning capability.
Is there any planned verification for those?
Oh, plan what?
Verification. The storm surge warnings.
Yeah, well right, again, the warning is based on a 10% chance of occurring.
Okay.
So it's going to dramatically overstate where the actual flooding is going to occur.
Okay.
But certainly that'll be looked at to see where the flooding occurred. And the basic idea is you don't want flooding to occur outside of the warning area. If that occurs in a significant amount, then you've done a bad job. So, but by design, it's going to overstate how much flooding actually occurs, because it's based on a 10% chance. Okay, let me go back a couple more things then. So one aspect at the Hurricane Center is the coordination of the forecast. So it's not just our forecasters like Richard Pash or Jack Bevan acting in isolation. It's coordinating the forecast with, for example, the Storm Prediction Center. So any tornado forecasts associated with the tropical cyclone are done by SPC, and we include that in our products. Likewise, for any rainfall forecasts, the forecasters here at WPC provide both text as well as graphical information about where excessive rainfall could occur. So about an hour before the advisory goes out, we have a coordination call, and you might have seen up in the operations area there's a brand new video teleconference set up that are supposed to replace these antiquated 1970s era phone lines. So we're hoping to make use of that soon. One other aspect to what we do at the Hurricane Center is the international coordination. So we're the regional specialized meteorological center that's responsible for providing forecast information for hurricanes for every country in the Caribbean and Central America. And an example of that is Hurricane Dean from a few years ago that went across the Caribbean, and each of the colors flashing on or off are tropical storm, watcher warning, or hurricane watcher warning. And the idea is that we provide the big picture forecast for the next 5 days, but each country's meteorological services are responsible for their own watches and warnings. So in actual practice, what will happen is we prepare the forecast, and let's say Dean is threatening Jamaica. We would pick up the phone and call the forecasters in Kingston, and we go, "Hey man, there's a hurricane coming. You want to watch a warning, man?" Well, maybe we won't use our bad Jamaican accent, but we have a great relationship with all the forecasters, in part because we have a WMO training class every spring where we bring in a forecaster from every country. And so it's an opportunity for our forecasters to get to know them and vice versa.
What's the time step? This is
6 hours.
6, okay.
So you can see there's changes almost every 6 hours. So it's a lot
Yeah,
of coordination.
Trying to get an idea of, how quickly they would warn, like, for example, the contaminants law.
Yep. Yeah, in general, the watches are 48 hours, and the warnings are 36 hours before the impacts begin. So in addition to the coordination internally and externally, the communication aspect is crucial. Unfortunately, we've had many folks that are wonderful communicators and had the opportunity to make sure that it's the same message. Studies have shown that if people hear conflicting information for hurricanes, they don't act. Sometimes not acting is the best choice, but often you do want to invoke a response. And so we need to make sure that we're communicating the same through the WFOs, through the National Hurricane Center, and through our partners in the Broadcast Met, as well as what we have on our website. So we want to make sure that the information is understandable for people to take action. In the off-season, we keep very busy between planning for the next hurricane season with new products, getting a chance to look at, for example, the newest model runs from GFS to see how they perform for hurricanes, as well as the outreach to the emergency managers. And so it's crucial that we convey to them what information can we tell you and what can't we tell you. Some emergency managers would love for you to make their decisions for them about who to evacuate, what schools to close, and what tourists to go home. We can't do that. It's not our job. So we need to make sure we can let them know what's available. So an important aspect for improving our forecast has been over the last over 10 years is the Joint Hurricane Testbed. And the idea is there may be research that's been demonstrated. This is an example from the Naval Research Lab or NOAA research or universities like University of Miami. How do we get great ideas in the research side into operations, either in the National Weather Service as a whole or the National Hurricane Center? So the Joint Hurricane Testbed has been a great opportunity to help get that over the hump, to get it into operations. Because great research doesn't get into operations by osmosis. It takes a lot of effort. So an example of a successful project were the wind speed probabilities. They are funded in large part from JHT resources. And to me, it's an incredible new product for folks. I already discussed the hurricane storm surge watch or warning. And again, that's operational this year. And we'll see if we have to invoke it. One other new product that is debuting this year is for potential tropical cyclones. So this is before a storm has formed. And the idea is to provide a track, an intensity, and a size forecast before formation. So let's say we have a disturbance in the Gulf of Mexico, high risk of formation, 80%, and it looks like that if it forms, it's going to cause tropical storm conditions before 48 hours. In the past, we haven't had a venue or an ability to send a tropical storm watch or warning before formation. So this allows us to make an official 5-day forecast and issue, along with the WFOs, watches or warnings along the coast or inland. So it's a new service for the public, and the way we're going to do it is, the regular tropical storm watch or warning is going to be used. So watch is tropical storm conditions possible within 2 days, warning expected within 36 hours. And the way we call them are potential tropical cyclones. So the first one would be potential tropical cyclone 1 if we use this stage. We're not going to use this over the open ocean now. It's just going to be for ones that will be impacting land within 2 days. An experimental product that's going to be available on our website this year is the time of arrival. It's using the wind speed probabilities to help inform residents on the coast or inland when might they have tropical storm winds start. And we're going to provide it in both 50th percentile, most likely, but also earliest reasonable time of arrival. So again, if you're an emergency manager for Charleston, you want to know, well, when are we expecting the winds to start so they can get all the preparations done? But when is the earliest it could reasonably begin? So they know they kind of have a bounded time frame of when to prepare. So we're hopeful that this will be a useful new product as well. And it's experimental this year. One last product that I'm hoping to get a chance to move forward in the future is doing wave height probabilities. So Joe Sinkowitz, Arun Chawla at EMC, and I have put together a proposal to try to provide this, not just for hurricanes, but for all the Weather Service area of responsibility and for all time of year. And the idea would be to make an analogous product that instead of have wind speed probabilities, use wave height probabilities. And the basic concept would be have several hundred ensemble members from the Monte Carlo run, use that to drive a second generation wave model and to get significant wave heights for several hundred different runs. So it's got to be a fairly simplified model. You could not use WaveWatch 3. And the idea is then for whatever threshold you would be of interest, in this case the container folks for the merchant marine vessels, they only care if it's really big wave heights. So in this case, 24 foot would be the example. The area in gray is the 50th percentile of 24-foot waves. But perhaps they want to be very risk averse and stay out of where it's a 10% chance of 24-foot waves. So again, it's the user would have different criteria that they're interested in. Cruise ships might be the other way around. They may, instead of care about 24-foot waves, they may want to stay out of 8-foot waves because they don't want the passengers to start YouTubing everybody throwing up. So let me finish up, and then I'll take questions, and then I'll summarize. So this gives you an overview of who we are at the Hurricane Center and what we're doing, and some of the new products that are coming online this year and what we're hoping to in the future. But what we have to keep in mind as scientists there is that, in this case, you have a graph showing population rise over Florida. It's the same for the Caribbean or other states in the United States. And superimposed on that are the hurricane strikes. So we know there's decadal variability of when hurricanes make landfall. And in particular, we've had a lot of landfalls in the last decade and a half, and the population's been going through the roof. So obviously that correspondence between incidence and exposure means billions and billions of dollars of damage, but also, more importantly, people could lose their lives. And so we have to remind ourselves, it's not just charts and graphs and numbers and statistics and physics, it's communication, and make sure that people know what can occur so they can take the right action. And believe me, with all these millions of new people in Florida, there's a lot of clueless families that may not know what to do. For example, this family is really clueless. And look at that shirt. So don't tell my wife I showed this picture. It's so cute though, because it represents 3 different generations that have to be ready for hurricanes. Whether it's the grandparents, the young-ish parents, or the newborn baby. Something everyone has to be prepared for. And so it's our role in the Weather Service, our mission, to help safeguard life and property and help even clueless families like this get ready. So I'm going to stop here, ask to see if there's any questions, and I'm going to summarize real briefly. So if there's any questions, this kind of shows what we've accomplished in the last 15 years in the Weather Service and the National Hurricane Center for new products. So thank you. Are there any questions? Yes?
I have a question about the track models that you use.
Uh-huh.
So I'm a programmer downstairs. I'm not a hurricane specialist. So have the models themselves gotten more accurate over the years? And I was also wondering how long they take to run the model to completion and how often you restart them.
Yeah, the models have gotten dramatically better, and the track forecast errors decreasing by more than half in less than a generation attest that that's been an incredible accomplishment. So the models, it's a mix of regional hurricane models. There's the Hurricane Weather Research Forecasting Model, and there's a brand new one called HMON. I don't know what that acronym means. Help me, VJ.
It's Hurricanes Multi-Scale Ocean Coupled Non-Hydrostatic Model.
What he said. And there's also several global models. So we utilize the Global Forecast System from here. We use the European Center's ECMWF global model, the UK Met's office's model, and the Navy runs a coupled hurricane model called COAMPS that's very useful for intensity. So it's a blend of those for the track, the intensity, and the size of the storm. And still today, while the track forecasting is all global model and regional model based, the intensity forecasting is still more subjective. So there's still some statistical model that help inform the forecast.
And how long do they take to finish running and give you an answer?
Typically 90 minutes to run the model.
Wow.
And updated every 6 hours.
All right. Any other questions? Yeah.
So, okay. Like we have the intensity gauge from satellite, right?
Yes.
It work. And we also have the flight.
Uh-huh.
We get the real, measure the real wind, right?
Yes.
If the two guys are not match, which one you trust?
Oh, well, if we have in situ information, that's certainly what we emphasize more. Yes. And having the aircraft it gives you nearly perfect position information, very good intensity information. It still can't measure the entire storm all at once, so you're undersampling a bit, so you have to account for that. And then even the size of the storm, it's a little more problematic from aircraft, because you may have a diameter of 400 kilometers of tropical storm force winds, and the aircraft can't fly that whole thing all the time. So, but certainly, if we have aircraft reconnaissance, that's going to be weighted much more than the satellite. Yeah. Yep.
So can you say something about what you think about the Shout mission and the Global Hawk? You mentioned that stuff. I know there's that meeting, and that's planned to be. Is that something you guys want for the future, or is that are still evaluating the impacts of that? Where do you see that kind of going forward?
Yeah. Whenever there's new observational capability, there's two main uses. One is directly by the forecasters, and one is used by the models for data assimilation.
Right.
I can't comment on what the models need. No one at the Hurricane Center is a modeler, so we can't answer question number 2. But for number 1, though, we have to determine where's the center of the storm, how strong is it, how large is it, what is the structure, that is it a tropical cyclone, extratropical, or hybrid? So if we get additional information to help us answer those questions, then it can be of help. And thus far, the main benefit of the Global Hawk are the drop-ons that they've been launching. So for us, for our needs as forecasters, it can help a little bit with the size of the storm because it typically go out farther than the reconnaissance will. But we won't use it directly for other aspects for the most part. I mean, there may be some forecasters that look at individual soundings, but the main utility would be in how the models use it.
So I work with the high-rep radar, which
Uh-huh.
is on there, and you guys been evaluating that, but I wonder if you probably really just want surface kind of winds, but would you have use of winds that are in precipitation above the surface, or do you just only really care about the surface wind?
Nobody lives at 2 kilometers above the ocean.
Right.
So we care about what the ocean surface winds are. However, if those winds from the HIRAD or whatever radar system can help in the data assimilation for either the mesoscale model or the global model, then that's great. But use of it directly by forecasters, unless it can help us say, where is the storm, how strong is it, how large is it, what is the structure, or help us inform about the environment it's in, it might be difficult for us to directly use it. I could be wrong,
Yeah.
but
But you use like 88D Doppler velocities to look at centers and things. So,
we do.
so
we
what's
do.
wrong with using that same kind of product over open ocean?
Yeah, well, when a hurricane is close to the ocean, close to the coast, and it's within radar range, we use the WSR 88Ds to determine the center every 30 minutes, as well as what are the peak winds at the lowest tilt of the radar. And so we do make use of the radar in that aspect, yeah. It only happens a few percent of the time, though, for all the advisories we make use of. And by that time, all the preparations should be done if it's in radar range.
Do you use the radar for the P3? Much?
We look at it because we can see the structure. I mean, for example, is a concentric eye wall forming? Because either radar or microwave imagery is often the first indication. So we use that qualitatively. Yeah, it's useful. And we're hopeful to get a more reliable data source from the nose radar from the C-130s. Right now, what they do is they take a picture from their radar scope or screen, and they phone it. They send it to us by phone. That's how we see what the C-130s are doing. So hopefully that'll be a little more automated in the future. Yeah.
Probably time is running out, but I have 2 questions, one technical and one programmatic.
Okay.
The first technical question, you said you are going to name the potential tropical cyclones as 1, 2, 3.
Yes.
How do you then address the just formed tropical cyclones? Are they going to be sequenced or?
It's all going to be continuous. So, for example, we've already had the A storm back in April. I forgot what it was. So the next system, whether it's named as potential or actual, is going to be 2. And if it turns out that we issue advisories, right, if we issue advisories on potential tropical cyclone number 2 and it doesn't form, the next one we would be writing advisories on would be 3. So we're done with 2. So just to keep it simple, yeah.
Just to make sure we are ready for that kind of a
Okay.
thing.
Yeah.
So
Second
you can
question,
put this in TC Vital?
I'm sorry?
Put this information in TC Vital?
Oh, yes. Oh, yes. Yeah. Yeah. Yes.
So maybe it's a tricky question. You may not answer it
Okay.
if you don't want. The change in leadership
Uh-huh.
at Hurricane Center.
Has there something happened in Miami?
Well, you are here, luckily, for the past few months.
Yeah.
What do you think you guys, I don't know. I don't think there will be any big change in the way things go there, but are you guys prepared for, James Franklin retiring and Ed now stepping out?
Right. Ed Rappaport has been named the acting director, and he's been working closely with Bill LaPenta to put together a plan to get us through the hurricane season. And so the plan is that Ed is acting director, Mark DeMaria is acting deputy director, Pablo Santos from the Miami WFO is acting technology science branch director, and Mike Brennan is acting hurricane specialist units branch chief. So yes, we're doing a lot of musical chairs, but the plan will work and we'll get through the season, and then hopefully they'll start filling those vacancies soon. So let me stop and just summarize, and then show one last slide. So just to summarize, I wanted to make sure you understand what our mission is. You know, we're an operational agency, and we're committed to reducing property loss and helping people safeguard their life. It's becoming more difficult because of the increased risk, where you have the incidence and exposure corresponding. And then lastly, we've been fortunate that, you know, even though our forecasts are never going to be perfect, you know, we're pushing more the probabilistic impacts of surge and wind, and we're hoping to work with WPC on probabilistic rain as well. So wanted to say thank you, and also just to appreciate the opportunity I've had to work at WPC and a little bit at OPC with Dave and Kathy and Jim and Joe and Darren and Greg. It's been a wonderful 2.5 months here in College Park. So thank you very much. All right. Great. Thanks. I appreciate it. Yeah.
So, can I post this one from
Of course.
YouTube?
Oh, yeah, yeah.
And also I recorded this one.
Sure. What's your name? Oh, good to meet you. Yeah, good to see you. Yeah, thanks. Yeah. Appreciate it. Yeah. Steve Baxter. Oh, Steve. Yeah. Nice to meet you. Oh, okay. I hope I didn't put you to sleep. Oh, sure. Yeah. Good to see you. Thank you.
We're talking about evaluating dynamic code with people similar issues in private scales. How to use ensemble spread in terms of probabilistic forecasts. Have you guys done some of that